అంతేనా బ్రా? అమ్మా చెప్పు ఏంటి?
Good morning, sir.
Yeah, good morning. Good morning, Dr. Purnima.
Thank you, sir. So, a warm welcome to all the ladies and gentlemen. Today we have with us an eminent speaker, Dr. Sitanshu Sahu, sir. Sir is going to throw a light on the application of this optimization. So far, we have learned about the technical, theoretical knowledge about what are the techniques and various types, what is the procedures and all. So today, sir will give us brief introduction about how to identify the particular system identification, which is very useful for the particular wireless channel estimation and wireless equalization and all. So I request all the participants to be take a notes from the sir's class. I request Vaishnavi ma'am to introduce sir. Thank you, sir.
Good morning, sir. I'm very happy to introduce you today.
Hello, I can't hear any sound.
Sir, can you hear me?
Yeah, now I can hear, but it's very low.
Can you hear me now, sir? Am I audible? Am I audible?
Yes, please carry on. Should I start?
Good. Sir, I'll just give introduction.
Okay, so I'm not getting it clear.
Dr. Sitanshu Sahu, sir, is presently working as an associate professor in Department of Electronics and Communication Engineering at Birla Institute of Technology, Ranchi. He has received PhD degree from NIT Rourkela in 2011. He has completed postdoctorate from Oklahoma State University in 2014. He has been recipient of DFAIT GSEF Fellowship from Canada Government in the year 2008. He has published more than 75 research papers in reputed referred international journals and conferences with more than 750 citations and H index of 13 and I index of 10 of 17. He has been active reviewer in many reputed journals such as IEEE, IET, Elsevier Science, Springer, Taylor and Francis, and Biomed Central. He has completed several research projects from DST, MHRT Government of India, and JCST, Jharkhand Government. He has chaired in many national and international conferences. His research area includes signals and systems, signals and image processing, bioinformatics, machine learning, and computer vision. We welcome you to today's session, sir.
Yeah, thank you, ma'am. Thank you. Thank you so much for such nice introduction. So, let me share my screen and let you know whether it is clearly visible to you or not.
Yes.
Is it visible?
Yes, sir.
Hello, can someone confirm me? Is it visible, my slide?
It is visible, sir.
Yeah. So today I'll be talking of optimization in system identification. So basically, what is system identification? What is its importance? And how optimization being used to identify a system, unknown system. And I'll be throw some light in a basic optimization techniques so that it could able to know how you will be applying the optimization methods in the system identification program. Okay, and stop me at any point of time if you face any difficulty understanding anything that I'm talking of. You can stop me anytime. Yeah, so what is a system identification, especially about? So system identification is nothing but finding out some statistical methods to build a mathematical models of dynamic systems from measured data. So if a dynamic system is there, so we only know what is the input is there and we observe its output especially, but we don't know what is happening inside this, what is the dynamics, okay, how the system governs the output, okay, from a predefined input, right? Okay, so like if you could able to model or find out a mathematical formulation of that dynamics, then we say if that input x is provided to the actual system as well as my model, then my model will give the same result or same output as the system, the physical system it provides, right? So that means we say that we identify the behavior or the characteristics of the physical system. Right? So that is nothing but we say we have mimicked the way the dynamics of the physical system is working. Right? So this is called a system identification. So under the similar situation, if you look at these two figures, if the physical system is system 1 and this system 2 is my model, basically this is my mathematical model, right? So if the input x is provided to the physical system, that is system 1, right? And suppose I'm getting y1 as my output, okay? And the same input I'm providing to my model, right? This could be a mathematical model, this could be analytical model, any kind of statistical model could be. So this same input when I provide to the model and I'm getting the output as y2, okay, in the same scenario, in the same condition. If y1 and y2 is same, okay, y1 equal to y2, then I'll say system 1 equal to system 2. Okay, system 2 is nothing but my model. Then I say I have mimicked the behavior or working of the system through the electronic model, okay, or the mathematical model. Then I say I have identified the behavior of the model. That's it. That's the system identification problem. Okay. So what is the system? Basically, the output of the system depends on its characteristics or its transfer function or its coefficients. Basically, define any physical system through its characteristics. When I say a system, that could be any kind of physical devices, right? Or any kind of different the devices basically. So suppose we take the example of a bulb. Okay, so if I give a certain amount of current and voltage, so it is giving me some kind of a luminous intensity. So that's the output that I observe, right? Similarly, if I look at a physical system as a fan, okay, a motor, or especially a robot, right? So if I give certain quantity of input, then I observe some of the output in the physical system. Basically, it is coming out. So we only observe the output. We don't know what is happening inside this. What is happening inside the fan? We don't know what is happening inside the robotic, right? We don't know what is happening inside the motor. Okay, what is the dynamic of the system? So only we observe the output. Okay, so Now our goal is to identify from the observation, the output observation and the input. Can you define some mathematical relationship between these two, input output that will, especially represent the behavior or the dynamic system, the dynamic representation of the behavior of the system, right? So that is nothing but basically the system identification. So the physical system basically can be, it depends on its characteristics or its transfer function or the system coefficients. Those are the governing parameter of the physical system, right? So in general, the output of the system can be represented as a function of input samples and the system coefficients, basically. So if I mathematically represent the output that yk at any time instant k is nothing but a0 x of k, a1 x of k minus 1, a2 x of k minus 2, like that. Okay? So I'll take certain, certain past values of the input x, right? And these past values or the delayed of the input signal multiplied with certain coefficients a0, a1, a2, right? And that gives me the current output, okay, yk. So that is the mathematical system. Basically, we represent in any kind of physical plant or physical system, right? So now our goal is to define this a0, a1, a2. So certainly, if you could able to determine the parameters a0, a1, a2 up to an, right? So that actually governs the behavior of the physical plant or the physical system. Okay. So that's our aim, is to determine a mathematical model for an unknown system by observing its input-output data, okay, using a suitable technique. So we'll be discussing what are the suitable techniques that we could be applied to find out the this system parameters a0, a1, a2 up to a, right? So that means they determine the model coefficients. Once we identify these models, or we approximate these model coefficients, that AK parameters, then we say that we have identified properly the system behavior. Okay, that is nothing but we call the system identification, right? For example, if I give an example like a spring mass damper system, so here the mass is connected to a basic structure. Okay, so if I give a force, that force will pass through this spring, that will be this one. The spring is passed to the spring, and it will apply to the mass, so that there will be displacement happens in the mass. Okay, and during the time that the displacement of the mass also going decaying, is called a spring mass damper system, a mechanical system, very widely used mechanical systems. Now, if I represent a mathematical formulation of the damping of the displacement of the mass, I can represent the mathematical formulation as m d square y by dt square plus c dy by dt plus k yt equal to f of t. Okay, so f of t is the force applied to the base, right? And yt is nothing but the output of the mass or the displacement of the mass. So displacement is nothing but that we observe as output, right? And m is the mass, amount of mass, and c is the damping coefficients, and k is the stiffness constant of the spring, right? So this is the mathematical formulation of the displacement of the spring mass system, right? So if you could able to derive the solution of this equation, that will give me the complete dynamic behavior of this spring mass damping system, right? Okay, so now to identify the behavior of this spring mass damper system, so we can design a model, okay, equivalent model of this equation that will give me my displacement yt as equal to b into f of t minus 1 minus a1 y of t minus 1 minus a2 y of t minus 2. Okay, so I'm again also getting a second order equation over here. So now my unknown parameter is b, a1 and a2, right? These three. So if I could able to find out or approximate these three parameters in a suitable way, then I'll say I have identified or I forecast the displacement of the mass. Okay, so that means I'll say I have identified the dynamic behavior of the mass. Okay. So that's the spring mass damper system. And if I go to another example, it's called magnetic leviation system. How do you identify this magnetic leviation system? Basically, so what is the main magnetic leviation system? So here there is there is a ball is there which is placed in the space. Okay, and above the ball is there is a magnetic field. Okay, so that magnetic field is created by providing certain amount of current to a coil, right? So that will create a magnetic effect, right? And that will be the force will be the magnetic force will be upward, and there will be a gravitational force that is downward. So that is m into g. So this ball has to be dragged towards the downward by using the by the gravitational force, and through the magnetic force that ball is also it is attracted towards the up, right? Now this magnetic force and this gravitational force applied to the ball, if it is equal, okay, when it is equal, then and suddenly it is in opposite direction. Okay, so one is downward, another is upward. So that means that will nullify this force, and this ball which is placed on the space, now it will be hang on the space. Okay, so that is the magnetic leviation system. So the mass or the ball is now it is a floating. Okay, it will look like a floating on the space, right? So this is the magnetic leviation system. Okay, and if you look at the laboratory setup of the magnetic leviation system, okay, so here the ball is like this. So now you see this is hang on the space here, and the upper one is the electromagnetic field generated by supplying some current. Okay, and then the downward will be the gravitational force, right? Now, what happens now if I give a little bit thrust on the ball? Okay, so if I give a little bit force on this side or this side, okay, on the upside and the downside, so there will be a little bit, a little bit disturbance on the force that is, set off the magnetic field and the gravitational force. Okay, so then there is a chance that the ball may fall down, right? If there is a little bit a change in the force, right? Okay, so now the disturbance, although the disturbance is provided, now what will happen? There will be a controller. Okay, so there will I'll design a controller, and that controller is to provide a certain amount of a change in the current to the magnetic field, okay, to the magnetic coil, so that the magnetic force that is generated on the upper side, so that will be nullify the gravitational force that is coming downward, right? So that's the arrangement of the magnetic field, right? Now, if I put this as a system, overall system, the dynamics of this leviation system, I could identify what is the dynamics of the magnetic leviation system. Then, once I identify this, the dynamics through my model, okay, that model will be used in the controller, okay, and then I give some amount of disturbance to the system, and then my controller has to control the amount of current flow coming to the magnetic coil. Okay, so that's is nothing but the entire system. Okay, works. So basically, I need to identify what is this magnetic leviation system. I'll generate a particular model, electronic model for this magnetic leviation system. So if you look at the magnetic plant, so its transfer function is defined by GPS equal to delta x b by delta u. So this is b by a square minus p square, and this is the value of the transfer function basically. So now when I say identifying the system is nothing but I try to identify the transfer function of this maglev plant or the maglev system. Okay, so once I identify the system, then I could use that system to the controller to control the disturbance coming to the system itself, right? So how we do this? If I replace this magnetic leviation system through an electronic model, okay, so then if certain amount of input they provide, okay, to the magnetic leviation system, what is the output? Okay, what is the output that I am getting across the magnetic leviation system? Okay, if I could able to get the approximation of this yk from my model, then I'll say the dynamics of the maglev system is identified through this model. Okay, so that is nothing but we call the system identification. We identify the behavior, the way it works. Okay, the way the dynamics of the maglev system is happening, so we could be able to identify through this model. Okay, so that's my aim. Okay, that's the aim of our object, the system identification, right? So if any kind of physical plant is there, if on certain condition, okay, in a similar condition, what is the input I am providing? Okay, if I am getting the output across the physical plant is same as the output that I am receiving across my model, then I say I have identified the characteristics or the behavior of the physical plant. Okay, so this could be a blast furnace also. This could be a robot also, right? This could be under mine also, right? Okay, under earth also. What is there? What is the response from the inside the earth? The earth system could be my physical system, right? Then I could identify its behavior. Okay. So that's is the system identification task. That's all about the system identification. Now, question is how I should go on defining my model. Okay, so that will behave or that will mimic the behavior of the physical plant, right? So the system identification flow graph is like this. So first we have to collect some experimental data. Okay, so we do the experiments on the physical plant or the physical system by providing some inputs. Then I'll get some output. So that is nothing but my experimentation part. Once I have the data, okay, so then I'll choose a model structure. Okay, so I'll select a model structure. That model could be any kind of mathematical model, any kind of adaptive model, right? Any statistical model, right? Machine learning model. So there will be several modeling structures available. So we could now choose properly which structure will be better fit to the system behavior, right? I'll choose the structure. Then I identify the model in the sense that I go on finding out the coefficients of the model, okay, or the parameter of the model that will govern the dynamics of the system, right? Okay, so that's the important part. That is called, we say that parameter estimation or the identification of the model. Okay, and this identification will be look at the optimization problem. So here the optimization comes, right? So basically we'll go on finding out minimization of the mean square error. Okay, so when the error is 0 or the reduced to a very small value, then we say that the model output is equal to the experimental data or the physical system output, right? So that is called your model identification, right? Once I identify the model, then I'll go on validating or testing the model, right? So if I provide some input to the physical plant and to my model also, is it coming same? Okay, if it is coming same, then it is validated. Now the model is ready to deploy. Okay, so now meet the criteria, right? If the output of the model and the output of the physical plant is coming same, if it is yes, then end. Okay, so now my model is identified. If no, then I'll go back again to the loop by changing the structure itself or by changing some parameter of the structure. Then again identify the parameters, then again validate it. Okay, so until unless I get a proper validation, I'll go on into this loop. Okay, so once I found my system output and my model output is same, then I'll stop this, and then I say that I meet the criteria and my model is ready. So that means the plant is now identified in a proper way. Okay. So now let us look at what is the entire structure of the system identification problem. Okay, if you look at the system identification, it's nothing but this is my physical system. Okay, so this is my physical plant, right? This is my physical system, right? And then this input is provided to the physical system, so I'm getting some output here. and the output also may be contaminated with some noise, external noise, or some noise inside the system itself, right? Okay, so I can model it as like thought of as some noise is getting added to the output of the system, right? Then, on parallel to this physical system, so I go developing a adaptive model or filter, okay, so which will go on recognizing the behavior of the physical plant or the physical system, right? Okay, we need to identify the physical system, right? So what is the output that coming across the physical system? It is yk, and then the output of our electronic model will be y cap k. So it's the approximation of the y output, right? Then we'll have a comparator over here. So we'll compare the actual output and the model output, right? So initially they won't be matched. Okay, so there will be used mismatch. So there will be generation of error, right? And this error will be used with the adaptive algorithm. Okay, and this adaptive algorithm try to change the parameters of the adaptive model. Okay, the parameters of the adaptive model in such way that whenever next time a certain input will come, okay, to the physical plant, and then this the output yk will try to be approximate by this y cap k, so it will be more near. Okay, so then whenever we certain sample, after passing certain samples, we will say that my yk is almost equal to y cap k. Okay, so that means the error will be 0. Okay, at that time I'll say my model is ready, or my model identifies the system behavior. Is there any query? I hear some noise. Does anyone having any query? Okay. Probably it is. Yeah, now it is better. Okay, so that means when I say my electronic model output y cap is equal to yk, so at that time this error will be 0, and I'll say my system is equal to the physical system. Okay, the electronic model is equal to the physical system. Then I say I have identified the physical model. Okay, so this is the entire structure of the system identification task. Okay. Now the central part is nothing but how we are designing this the adaptive model or the adaptive filter, and what is the adaptive algorithm all about, right? Okay, so because this part is our electronic model, right? So this is our model development part. Okay, so now I've spent a little bit more time on adaptive model, how we can look at this adaptive model as optimization task. Okay, then how optimization, different optimization algorithms will be used to identify the physical system. Okay, so what is the adaptive filter? So adaptive filters are essentially some kind of digital filters with self-adjusting characteristics. So it adapts automatically to the changes in the input signal, right? So if the what is the input signal is coming, okay, so it try to change its behavior. The electronic model, the adaptive model, try to change to the behavior so that the output of the physical plant and the output of the electronic model will be towards they will be similar. Okay, so that means the adaptive model is a changing characteristics. Okay, so in the sense that I'll say the parameters of the adaptive model is going to change, okay, according to change in the input and according to change in the environment. Okay, so that's why its name is adaptive. Okay, so it has an adaptive adaptation algorithm that means to monitor the environment or what is the change is happening in the input, right? Because the input is very dynamic in the actual system. The inputs that could be of a stationary type, right, or could be of non-stationary type. Okay, so this non-stationary, it is difficult to find particular mathematical relationship of the output and input, right? In that case, so my model also has to be adaptive, okay, so that it could sense the change in the environment, it change in the input, and it will vary the transfer function, the filter transfer function accordingly, so that it will give me a response is very near to the response of the actual system. Okay, so based on the actual signal received, it attempts to find the optimum filter design. Okay, when I say optimum filter design, So that means the error generated across the comparison of the actual output and my model output, it has to be minimal. Okay, when it is minimum, then I say I have identified the system properly. Okay, and the adaptive filter can be classified into many ways. One is the linear filter, another is the non-linear filter. Okay, so in the linear filter, the estimate of the quantity of interest is computed adaptively as a linear combination of the available set of observations applied to the filter input, right? So that means here the quantity of interest is nothing but my output, okay, the output of the physical plant, okay. So then my output of my model also, if I could able to design as a linear combination of the available set of observation, that means my input, okay, some set of past input values, okay. If I go on combining them with a suitable multiplication of parameters or the coefficients, which is a linear combination of the input values, okay, so that will give me the output, okay, output of the model. So that means we call it the linear system, okay, it's a linear model. So when the relationship of the output of the model with the set of inputs available, okay, if they are the relationship is non-linear, then we say it is a non-linear adaptive filter. Okay, and example these neural networks. In the neural networks, obviously use several activation functions. Okay, so non-linear activation function, and through that it gives me the output of the structure, the model. Okay, basically, so it is a non-linear behavior. Okay, neural network. Then Volterra filter also. This is another type of non-linear structure of adaptive filter. Okay, so especially the adaptive filtering is composed of two things. One is the filtering process, another is the adaptive process. What is the filtering process? It designed to produce an output in response to a sequence of input data, right? What is the input is coming to my system, okay, my model, okay, so that means it will produce some output. Okay, what is the change is happening in the input data, right? That's the filtering. Okay, then simultaneously there is an adaptive process also. Its purpose is to provide a mechanism of adaptive control of the adjustable set of parameters, because my model, okay, so I have the parameters or the coefficients, okay, that coefficient has to tune up, that coefficient has to be changed, okay, because the input is getting changed every time. Okay, so and then also my filter has to adjust to the change in the input as well as to the change of the dynamic behavior of the system, physical system itself. Okay, so that it could identify the behavior of the physical system properly, right? Okay, so there is a filtering process which will filter out the input, and there is an adaptive process which will go on adjusting the parameters or the coefficients of the model. Okay, so these two processes work interactively to identify the behavior of the model proper way. Okay, so if you look at a linear filter, linear adaptive filter, okay, so especially the model, I could design an adaptive digital filter. Okay, so here the input will be x of k. Okay, so I'll provide this x of k to my model. Okay, so it will generate my output yk, right? That yk, it will be it will be compared with the desired signal, okay, because I want to have my physical system is the desired k dk, okay, and I want my model output yk should be equal to the dk, right? So there will be a comparator, so there will be generation of error, and that error will be used in the adaptive algorithm. That adaptive algorithm is going to change the parameters and the coefficients of the FI filter, so that whenever next time a sample of x of k comes, so it will be more close towards the a desired sample, a desired element at that particular time instance, so that the error will be going to reduce, right? Okay, so this is the entire design of adaptive filter, FI adaptive filter. So this is a linear filter, because this FI1, okay, so the output yk is nothing but is a linear combination of the past p values of the input multiplied with its coefficients, right? Okay, so that's why it's a linear filter. Okay, so I can use here also a non-linear filter, just like a neural network, just a Volterra filter, several other nonlinear models also I can fit into this, right? But mostly we'll use the FI filter as a simplistic model for the adaptive filters, right? So if you look at a little bit more details, so I have a transfer function of the physical plant over here. Okay, so this one is my physical plant, for example. Okay, so I define its transfer function. Okay, its object as this one is its object as multiplication of this past values of x of k with its coefficients a1, a0, and a2, right? Okay, and then it is adding up together over here, then added with the noise, so that is giving me the behavior or the output of the physical plant. Then when I say I model the plant especially, so I'll design a adaptive FI filter over here of same structure. Again, also I put a FI structure over here. The same input is also providing to the model. Okay, and that model initially it will give me some output yk, and after comparison with the actual plant output, so will generate error. That error will go fed into the learning algorithm, and that learning algorithm is going to change this parameter of the model. Okay, so initially the model parameter will be very less, or we have initial guess, and this parameter has to be changed adaptively. Okay, so that as the samples pass on to the plant and pass on to the model, so this y cap k will be more approximate towards yk, and thereby the error will be reducing towards 0, right? Okay, so that is called the adaptive filter structure and adaptive filter or adaptive system identification, right? So that means here I say my AK here EK is nothing but this is YK, the desired plant. Okay, so the actual output of my plant is nothing but YK and minus of Y cap K, right? At kth instant time instant, right? So now whenever my error is going towards 0, okay, when the error is 0, so at that time I'll say okay, yk minus y cap k, it leads to yk equal to y cap k. Okay, so that means my system behavior or my the electronic model, the model of the output and the actual plant output will be equal. Okay, so at that time error will be 0. Okay, so that means this is nothing but looking at the optimization problem. I can see the error. Okay, error is my cost function. Okay, I need to minimize the error. The more the error is less, the better the approximation of the model output towards the actual output of the system. Okay, so that is nothing but a optimization problem. Okay, so here it's nothing but we are trying to minimize the error. So that's the optimization framework. Okay, so then when we have coefficient adaptation, okay, so we need to adapt these coefficients, which is initially we have initial guess, okay, or we can start off with 0, okay, then we go on changing the values, okay, based on the change that is happening inside the environment, right? So once you go on changing this weights, or we say that the change or the adaptation of the weight parameter or the coefficients of the model. Okay, so that my approximation will be more and more better towards the actual output of the plant, right? So that is called a coefficient adaptation or adjustment of the coefficients, right? So the principle behind determining the coefficients of the filter is to maximize the statistical correlation between the desired signal and the coefficients. Okay, so the correlation of the coefficients is AK, A0, A1, A2, okay, A0 cap, A1 cap, A2 cap, okay. So the correlation of this filter coefficients with the desired, okay, yk, if they are same, means the correlation is maximum, then we say that my physical model is being properly identified. Okay, so typically this is done by minimizing the correlation between the error signal and the filter coefficients. Okay, the other way I can say we minimize the correlation of the error and filter coefficients. Okay, so if the minimizes the correlation is minimum, then I say the error is getting separated. Okay, so it is totally filtered out. The error is getting separated. Now my model output will be equal to the plant output, right? So in that way, the adaptive filter works. Okay, so that means when the error signal decreases in magnitude, so that slows down the movement of the coefficients, and we say that we are converging to a solution in the sense that the error will be almost zero at that time. Okay. So then, as I said, the system identification is nothing but we can thought of it as the optimization problem. So here, the objective function of the optimization is nothing but we are trying to minimize the square error, the square of the error. Okay. So when you minimize the square of the error, then you say that our model electronic model output is equivalent to the actual plant output. Okay. So this is nothing but a optimization problem. So there is several ways to optimize objective function, that is minimizing the error square function. Okay. So how do you know whether the system is perfectly identified or not? Okay. How do you know? So if the transfer function, the plant or the physical system is defined as Pz equal to A0 plus A1 z to the power minus 1, A2 z to the power minus 2 up to An z to the power minus n. So this is nothing but a FIR structure. As I said, the adaptive filter, a plant also we can design as a FIR type or IR type. Okay, FIR system or IR system. So basically we use the FIR1. So this is the physical plant is designed by the FIR system, right? And the parameters of or the coefficients of the plant is nothing but A0, A1, A2. Okay, and these are nothing but we call the impulse response of the system. Okay, so when we say we identify the system, that means we are trying to find out the impulse response in time domain, and in the z domain or the frequency domain, it is nothing but the transfer function, right? That is P of z. We identify the P of z. Okay. That means we are trying to better identify the coefficients because the impulse response lies in the coefficients. It is A0, A1, A2, A, right? Now, my model, electronic model, will also follow the same structure as a FIR structure, and then I'll have my unknown parameter of the FIR structure as A0 cap, A1 cap, A2 cap, up to An cap, right? Okay. So our goal is to identify this A0, A1, which is more approximate or is very close towards the actual value of the A0. Okay, A0 cap will be close to A0, A1 cap will be close to A1, A2 cap will be close to A2. Whenever this happens, then we'll say I have identified the behavior of the system to the coefficients of my model. Okay. So for a linear system, if the system, the physical system is linear, at that time we'll see when we have optimized the error square function and we have identified, then at that time we'll see that A0 will be equal to A0 cap, A1 will be equal to A1 cap, and An will be equal to An cap. So the physical plant parameters will be just equal to my model parameters. Okay, that is the case when it is a linear system. Okay, but it doesn't mean that always the system will be linear. So this could be of linear, non-linear system, very complex dynamic system. So at that time, so the model coefficients will be not exactly equal to the parameters of the physical plant or the physical system. Okay. So at that time, the system parameters do not match, but the response of the actual system or the physical system will coincide with the response of my model. Okay. So the output of my model will be the same as or equivalent to the output of my physical plant. Okay, in the nonlinear system. Then when it also occurs, then we say also we have identified the nonlinear system. Okay, so this is the testing or the way that you know that we basically evaluate whether the system is perfectly identified or not. Okay, so if it is a linear, then we call it the linear system identification. If it is a nonlinear type, then we say it is nonlinear system identification, right? Now let us look at what is the adaptive algorithms, because that is the main core part of this adaptive model design or adaptive system identification, right? So what are the adaptive algorithms? So most widely used adaptive algorithm is the least mean square algorithm, LMS algorithm, and nowadays also there's several dozens of nature-inspired optimization algorithms that could be also used to optimize the parameter of the model, right? For example, we can use the genetic algorithm, particularly SOM optimization, teaching learning-based optimization, now whale optimization, or differential evolution, ant colony optimization, bee colony optimization, BAT algorithm. There are several dozens of nature-inspired optimization algorithms are there, so we can utilize also those to to approximate my system parameters. Okay, the model parameters A0 cap, A1 cap, which will be equivalent to the or equal to the system parameters A0, A1, and A, right? Okay, so I'll go into a little bit description about the least mean square algorithm. What is the optimization framework? What is the algorithm about? Then we can go to this some of the nature inspired techniques, how these optimization principles can be utilized to find out the system, the model parameters. Okay. So the least mean square estimation of, or I can say the model, the optimization of the model parameter. Okay. So we do in the least square estimation. So it is nothing what we call the Wheeler filter. Okay. So in this filter, if you see, my model is nothing but this is the FIR structure. Okay. So as I said, this is my FIR filter, the model filter, which is equivalent to the physical plant also. Okay. So if the input is x of a, right, and this input is provided to the FIR system. Okay. So this is past one sample. This is past second sample. Okay. And this p minus one past sample, right? And this is multiplied with its coefficients w0, w1, w2, wp minus 1. Then it is added together, and that is giving me the output. Okay, so this is my model output, and this model output is again compared with the desired. Okay, so desired signal, and the error that is getting generated, and that error will be used, okay, to optimize this w0, w1, w2. Okay. Now, if I look at the error of the signal or the filter is nothing but EM. So this EM is nothing but DM minus YM. Okay, so DM is nothing but my desired signal. Okay, which is nothing but the output of my physical plant. Okay, physical system at mth instant or the mth time moment, and YM is nothing but it is the output of my model. Okay, my adaptive filter. Now this adaptive filter can be written as W transpose into X, okay? Because this W is nothing but it is the filter coefficients, right? W0, W1, W2, WP minus 1. Okay, so this is the vector of the coefficients, and X is nothing but the vector of my input signals, okay, which consists of the present input as well as the past P minus 1 past input samples, right? And this YN is nothing but summation k equal to 0 to p minus 1 wk into x of p minus square. So this is essentially the FIR filter, okay? FIR filter output, right? So I can write this in matrix form W transpose X. And now EM is nothing but DM minus W transpose X, right? So now this EM has to go to reduce as soon as the input sample go on into the structure. This EM has to reduce. Okay, so that means my objective is to reduce the error. Okay, the error, if it is reduced, then my DM will be nothing but equal to YM. Okay, so that means the Wiener filter try to find out a way to minimize the average square error. Okay, the average of the square of the error with respect to the filter coefficients. Okay, so if the square of the error is going to reduce to 0, okay, then we'll say that my system output yk is nothing but equal to my filter output, right? Okay, so that means to optimize this, we know that we need to take the gradient of this. The gradient has to be equal to 0, and then we find out the coefficients w. Because the basic mathematical formulation for finding out optimization, okay, problem. So now here we'll use the average square error function as the optimization. So average expectation of the E square AM is nothing but the expectation of DM minus W transpose X the whole square. Okay, so that means you can split it out as D square AM minus 2 into W transpose expectation of X into DM, and plus W transpose expectation of X into X transpose into W, right? So this is A minus B whole square. Okay, so you split out this one, A square plus B square minus 2AB, right? Okay. So if I look at this one, expectation of D square AM, so it is nothing but it is the power of the desired signal. So R dt of 0, so this is the power of desired signal. Okay, just just only the square of the individual element, then take the average of that. So this is nothing but the power. Okay. Now if you look at the second term, 2 into W transpose expectation of X into dm. Okay, so this is nothing but expectation of X into dm. So this is nothing but is the cross correlation. Okay, cross correlation of the input with the desired, cross correlation of the X into D. Okay, so that becomes RXD. Then the third term it becomes W transpose capital RXX of W. Okay, so RXXW is nothing but expectation of X into X transpose. So this is nothing but we say that the autocorrelation of the input X. Okay, so now it becomes this formulation. So RXS is nothing but the autocorrelation matrix, and RXD is nothing but the cross correlation vector, right? So now my error square, the objective function, it can be defined like this. Okay, so now if I make it to 0, okay, so this mean square, the average of the square of the error function, if it is 0, then I'll find out the formulation over here, and then you can get it what is the W parameters or the W coefficients of the model, right? Okay, so if you look at the error square, okay, the objective function, that error square with respect to how it is varying with respect to two filter coefficient W0 and W1. So if you look at this becomes a quadratic function. Okay, for example, I have a FR filter having only two coefficients W0 and W1. Okay, and then if I define error square, then again it is a quadratic function. And you look at the error surface. The surface of the error square looks like a bowl shape. Okay, it looks like a bowl, right? And the minimum value of the error square is nothing but this one. Where is the minimum? Less the minimum value of the error square. That is nothing but the optimum objective function at that particular value. What is the value of W1 and W2? I said W0 and W1. So this is nothing but my optimal filter coefficient. So I need to identify this and this. Okay, so that is nothing but my optimum filter coefficients. At that time, the error square is reduced to 0, right? Almost minimum, right? So the shape of the mean square error function is a bowl shape. Okay, bowl surface. Right? So and then if I need to find out the gradient vector. Okay, so the gradient vector has to be reduced to 0. Okay, the expectation of error square. Okay, so that has to be reduced to 0. So to find out my optimum value of the filter coefficients. So as I said, the gradient vector can be defined as delta W with respect to W. So I can take the partial derivative of error square with respect to W1, W0, W1, W2, and WP minus 1. Okay, so if I do that one, so that error square, derivative of the error square will be nothing but this one. Okay, if you look at the derivative of this, we are taking the derivative of this error square, the average of the error square function, and since there is no filter coefficients associated with this R dt 0, so it will be reduced to 0. Okay, the derivative of this will go on 0, and the derivative of this will be nothing but minus 2 into Rxt, and this one will be 2 into W into Rxx. Okay, so the same thing is written over here. Okay, so this is minus 2 Rxt plus 2 into W transpose Rxx. Right, now I have to put it 0 because this term has to be reduced to 0. Okay, so this is my objective function. This has to reduce to 0. Okay, so this is the minimum of the mean square error. Okay, minimum of the winner filter. Okay, the mean square error. So it has to minimum. That means if I put it 0 over here, so this term will come up over here. So this will be 2 into RXD. So it will be nothing but equal to 2 W transpose RXX. Okay. So then my W will be nothing but, so 2 to cancel it out. So this will be RXX inverse RXD. Okay, so that is written over here. This one. Okay, so this is my W. So W is nothing but my electronic model or my adaptive filter coefficients. Once I have this coefficient, that means at that time the error score will be 0. Okay, so the error will be 0 at that time. At the time, my yk will be nothing but equal to y cap k. Okay, so that means my filter output will be equal to the actual plant output, right? Okay, so that means I say I have identified the system. Okay, so this is called your least square estimation, right? In the least square estimation, so here I need to find out the autocorrelation matrix, take the inverse of the autocorrelation matrix, then multiply with the cross correlation vector. That will give me the optimum value of the weight, right? But the problem is here, this autocorrelation matrix, it requires a large, value of the autocorrelation function. Okay, so we need to have the large sequence of the signal available at a time, which is the biggest challenge, because in many times the real-time scenario we don't have infinite long sequence. So then approximating the actual value of the autocorrelation function is sometimes very tedious. Okay, so finding out this inverse of the autocorrelation matrix is very difficult. Yes, that's why we will go on finding out how instantaneously we can go on finding the optimum value of W. Okay, and that leads to another algorithm we call the least mean square algorithm. This is proposed by Woodrow and Huff in the round of 1959. Okay, so it is a computationally simpler version of the gradient search method of the least square filter, in which the gradient of the mean square error is substituted with the gradient of the instantaneous square error function. Okay, so instead of gradient of the mean square error, just like we have here, the gradient of the mean square error. Okay, so we'll have the gradient of the instantaneous value of the mean square error, right? That's the only difference. Okay, so here the first function is again the mean square error. Okay, so we'll find a gradient search procedure. We'll start off with initial guess of the filter coefficients. Okay, very small value or almost 0 of the initial guess of the filter coefficients. Then we'll try to find out the gradient of the instantaneous error. Based on that, we'll go on change the weight values little bit more. Okay, we'll go on delta change of the coefficients. Then again we'll find out the instantaneous value of the error square. Then again change the coefficients. Like that, we'll go on changing the coefficient until unless we see that the square of the error function is going to decrease towards 0. Okay, so when it moves towards the minimum on the surface, error surface, okay, to get the minimum gradient of the error, so estimated at every iteration. Okay, so whenever it is minimum, then we say that the weight value that we find, that is equivalent of this optimal value of this weight. Okay, which we are getting directly, right? Okay, so that is called your least mean square algorithm. You will see that. So the LMS will go on changing the weights at every iteration. So that means if W of n plus 1, the next value of the weight will be nothing but the old value of the weight plus mu into the delta change in the error square function or the gradient function or the objective function. Okay, so that is delta error square with respect to delta of m, right? Okay, so that is the instantaneous gradient. So this one is the instantaneous gradient. Okay, so in the instantaneous gradient of the square error can be written as delta of error square m with respect to delta w. Okay, so if you look at this error square, so this will be again d minus x transpose x, okay, square. Now you take the gradient of with respect to delta, this W, so that will leads to minus into 2 into x of m into em, right? Okay, so this is the gradient of the error square. Now if I replace this one here, so that my update equation becomes m plus 2 into mu into xm into em, right? So that means the update value of the tap weight vector. Okay, so this is the weight vector of the model of the coefficient of the model. So the update value of the model will be nothing but the old tap weight vector plus 2, okay, into the learning rate. Mu is the learning rate. Okay, so this mu learning rate is judiciously chosen from 0 to 1. Okay, and there is a fixed coefficient, and this x of m is the tap input vector. Okay, so x of m, so p minus 1 inputs, first inputs, that is becomes the vector, this x of m, and this em is nothing but the instantaneous error signal at that particular moment m. Okay, mf instant. So that gives me the weight updation of the model instantly. Okay, every passes of the input sample, the weight vector is going changing. Okay, so after certain iteration, we will see that the error square will be going towards 0.